So the next part is going to be about basically considering anisotropy as well as the material orientation and why this is very important for materials such as woven domains, which are of particular interest to NASA. In this first slide, I just want to show some of the woven domains that are usually used most recently by NASA as heat shield materials. This was a real micro-CT reconstruction for a particular design called ADEPT, which is an inflatable heat shield. So if we now zoom into some of the toes that are basically this collection of fibers along the weave, we can see that there is porosity going along the toe. And this determines that basically there is a variability in the material property along the toe. Even more so if we zoom in and now we have enough resolution to see every single fiber, we observed throughout our studies that this anisotropy basically carries out at multiple scales all the way down to the fiber level. A very critical component of our workflow for computing material properties, considering the anisotropy of these domains, is to segment out the woven domains. Basically, we want to have every single toe, having a different ID, and basically having them segmented out from the rest of the faces. So I've just listed here some of the reasons why it's important to have the woven domain segmented. For example, here I had a question earlier about detecting damages throughout a micro-CT. And this is basically one of the crucial steps for segmentation, is also to go inside the micro-CT and explore toe by toe if there are any flaws inside it. So something that we've been working on is a module called Detecto, which is made of a couple of different functions. One that allows you to basically manually segment every single toe inside your micro-CT domain. And this is what I'm showing on the bottom left, where you basically manually segment the toes in order to create training data to feed into an image segmentation deep learning architecture, which is based on an open source software called Detectron 2, which is by Facebook. And so this specific deep learning architecture is called a UNet, where you have an encoder and a decoder. Basically, the encoder gives you some interesting features about your micro-CT domain. And on the other hand, instead, you're basically solving your whatever target you're trying to do, which is in this case to segment out the different toes. And this is basically what the decoder part of the UNet is doing. And it's split up into several different heads, which are a term used in deep learning. In this case, we're doing panoptic segmentation, which means separating out both on a semantic level as well as on an instance level. What that means is that basically what we want to obtain is every single toe needs to have a single ID. So the two semantic classes that we have are in plane and out of plane toes. And on the other hand, the instance segmentation is how to give every single toe a specific ID. So this is some of the earlier results that we obtained. And this is the semantic classes and the instance segmentation. Then if I go into some of the results that we obtain, basically after you run the training, what you can predict is these labels throughout your slices of the micro-CT weave. And then by doing a simple approach to track the fibers through the depth, by checking how much they intersect in the depth, we are basically able to obtain labels that are continuous inside the depth. And so every single toe now has been given a specific ID. So once we have the segmentation done, and it's not necessary, but we have shown that it greatly improves our orientation detection. So I already mentioned earlier that we have some algorithms already implemented in PuMA, 3 specific algorithms to detect the orientation of the fibers as well as the toes or a weave. So the first one that we implemented is called the structural tensor, which is an image processing technique that directly works by looking at the gradients of these grayscales throughout the micro CT. And we basically are solving an eigenvalue problem by picking the direction in which the gradients is changing the least. And by the way, I also want to reference, we've published a whole paper about these three methods where you can see a lot more discussion about the theory as well as the numerical experiments. So the second part, the second algorithm that we implemented is called the artificial flux, which basically runs a thermal conductivity simulation throughout your material. So you impose a temperature gradient, and then you run basically the solver to converge the temperature. And in this case, we assign a conductivity of an artificial conductivity of 1 for the fibers or the solid phase, and 0 to the void. So what you obtain is a heat flux, basically. And let me replay this video for you. That the heat flux is going to be roughly aligned with the orientation of your domain. The third algorithm is based on a ray casting approach, where at every solid voxel, we basically shoot particles or rays in every direction. And then we pick out the direction in which the particle travels the longest, as you can see here. And that's going to be roughly aligned with your local phase orientation. So these three methods, I will give a brief code example for these three methods before jumping into the next section, which will be about the thermal and mechanical properties. But now let me pull up the video for this part. In this tutorial, I'm going to talk about the capabilities of PuMA in terms of detecting the orientation of a material. So depending on whether you're running C++ or Python, or PuMA basically, you're going to have access to different capabilities. So I want to clarify what you should be using. So starting from PuMA, the only orientation method that we've implemented in this is the one based on the structure tensor. The structure tensor is an image processing technique that is able to detect the orientation of minimal change of gradient in terms of the grayscale values. So I'm just gonna go ahead and press run for this one, and as it produces the results, I'm gonna discuss about them. So the first thing is I'm gonna import a 3D TIFF, which is from the datasets that are currently coming with PuMA, and specifically is the one that is the 200 cubed fiber form, and then I'm gonna volume render it. And so there it is, volume rendered it already. And in this rendering, I've intentionally left the grayscale intensities noticeable so that I can basically give you a feel of what the structure tensor is looking for. So if you look at, for example, along this fiber, you can see that the grayscales change the least, for example, inside the depth along this direction. So the structure tensor, what is computing is the gradient of these grayscale values, and then it's looking for the minimal change. So basically the minimal change will be roughly oriented along the fibers. So I'm gonna close this figure and let the solver run through the compute orientation ST, which stands for structure tensor. The input that you need to give is the solid phase. And so in this specific tutorial, I'm gonna export the workspace. So the orientation gets automatically appended to the workspace. And so in this case, I've just exported it to my downloads. And then I will visualize it using ParaView. I will import it, and as you will see in the drop-down list, you will both see data and data orient, which data will be simply the micro CT that we've imported. So I can threshold it again using the similar cutoff value as I did for inside PuMA. And so as you can see, here is our fibers thresholded, and then I can show the vector field that has been computed by running a glyph filter on top of this VTI. And so for the scale factor, I'm gonna put 0.5 e to the minus 5 in this case because of the voxel size. And then something else I'm gonna change here is how many vectors to plot, and I will put 300,000. And now ParaView is creating the glyph filter, and it will plot the vector field. And in this case, I'm coloring I will just color it, make it white. So as you can see, this is the automatically detected orientation on the micro CT data. And so as you can see, it's pretty accurate for this specific data set, since the grayscale values are pretty nicely visible. So I will now jump back to the PyCharm project, and I will show you how the next section that I've prepared involves basically running the other orientation algorithms that are only available through the C++ version of PuMA. So just to clarify, whoever is not interested in the C++ part, this will be a bit more advanced than the Python part, and I don't want to confuse anyone, so beware that this will be more advanced. So, by the way, this is currently running, so I'm just gonna talk over while the solver iterates. So the first part that I've added over here is the creation of two files that we need to compile our project. So basically, these are automatically created, and these are the CMake lists and the make all file. And then the third one is basically our PuMA example.cpp. So what you're seeing here in the Python script is simply outputting these files that we need for compiling the C++ example. So I will open up these three outputs just to show you how they look. So for the CMake, it just looks like a pretty standard short CMake, where you're basically linking your C++ file, which is this PuMA example C++, against the already installed library, which is basically specified over here. It's called libpuma. And then the second part is the makeall.sh, which is a bash file. The only thing that it does is basically creates the build folder, and then it runs the CMake, runs the make, and it installs this PuMA example. So this specific CMake was devised so that it will install this PuMA example all the way inside our Conda environment. So as you can see, I wanted to show you that if you go all the way in depth inside your environment, it will basically be inside the PuMA tutorial, and in the bin we have the PuMA example that I'm currently running. So the other part that I created here is just a function that calls this makeall, and then it runs the PuMA example executable that is created. And then the last one is basically I'm creating the C++ file that is right here. So let me just briefly talk you through what I'm running in this file. I'm running basically the three methods, again the structured tensor, but in the C++ implementation part, and then the other two methods that are the raycasting and the artificial flux. So as an example, I decided to run these three methods on an artificially generated sample of fibers. So in this case, we have the input to the generate random fibers function, and you can basically specify all of these ones are input details about the sample that you're about to generate. So to give you a feel, just to have basically a reference of what these inputs are, I usually reference them going to the documentation of PuMA, and then in here in the search docs I will paste the specific function that I want to run, and I will open it. And then here it's pretty small, but you can see the name of every single input. It hasn't been documented as well as the Python version, but you can still get a feel of what the inputs should be. For example, the sizes first of your domain, the average radius of the fiber, etc., etc. So then the second part is I'm exporting the 3D TIFF for the artificial fiber sample domain, And then I'm also exporting the correct orientation. Basically, since we're generating this fiber domain, we know a priori the orientation. So something that I can now visualize is these two files. So if I drag and drop, it will create an out folder inside which the CMakes, make all, etc., and also all the files that are generated are output. So I will drag and drop this inside PowerView and select the TIFF file, and then click apply. In this case, let me create a threshold of this. Okay, I'm gonna zoom out, and here is our threshold. Here is our domain, which I need to threshold by the correct threshold here. I'm putting 128 in this case. And here is our fiber domain. In this case, I'm also showing a capability that is not currently part of PuMA, which is the generation of random fibers with specified cross-sectional areas. So in this case, I both used, if I jump back inside the pie chart, I used the straight flower hollow input to the generate random fibers. So the cross-section, as you can see, is we have a hole in the middle of each fiber, and on top of that, the cross-section, it looks like a flower shape, which is more realistic to how these fibers actually look like. So the other thing that I can import is the correct orientation, which is output inside this VTK file. So drag and drop it inside PowerView, and now I can create a glyph again of this and select this, and let's see how it looks like. Okay, so here is our rendered orientation. Just FYI, I increased the scale factor and the number of samples. And so something else that you need to be aware of is that when you import a TIFF inside ParaView, you need to specify here the custom data spacing to just be 1, so that both the orientation and the TIFF will have the same size. So here is our threshold, and then on the bottom we have the correct vector field that was created. So let's check. Okay, it is completed for the 3 orientation methods. As you can see, if you get this, these are only warnings. The 3 orientation methods have output the 3 orientation estimations. So we can use basically the correct analytical solution for the orientation and benchmark how the 3 methods perform. And this is what I did in one of the papers that I published. So let me import these 3 orientations inside ParaView as well, and create like glyph filters for them. I will color them with different colors so that we can distinguish. And so there we go. So we have the 3 orientations that have been detected, a plot in the same window. So something else that we also analyzed, since this is not really decipherable like visually, we also came up with the function for comparing the different orientation fields that have been computed. So I would recommend to start with the structured tensor in Python. And so that's the easiest thing to run and the most user-friendly. If you need more advanced capabilities, I would then jump inside the C++. This completes the tutorial about the orientation. See you soon.